Hello, friends, and welcome to Unit 3, Lesson 4. We're going to discuss rates of change and slope. If you're watching this on the smartboard as a class, I hope it feels like I'm still here. If you're watching this with headphones or you're rewatching this on your own, just a reminder that you have the power to rewind, you have the power to pause, you have the power to mute me, fast forward, and do all of those kinds of things as it applies to what you know. All right, we're hoping that at the end of this lesson that you understand how to use rate of change to solve problems and to determine the slope of a line. All right, so the rate of change is a ratio. So remember, that's a comparison of two things. Notice how we've got that fraction bar down here. That on average, so it might not be exactly all the time, but on average, how much one quantity changes with respect to a change in another quantity. So you see below in blue and red ink, we refer to it as your change in y over your change in x. Y and x being the two different quantities that are changing. So I don't know if you've ever seen, but sometimes we use the Greek letter delta to talk about change in. So maybe you've seen delta y over delta x, which means your change in y over your change in x. And that is when x is your independent variable and y is the dependent variable. So this is when, again, your independent variable is on a horizontal axis and your dependent variable is on a vertical. So when we talk about some common rates of change, one that is probably near and dear to you as you learn to drive is speed, right? I'm sure if any of you have started to drive, mom and dad or whoever is practicing driving with you is probably on you. You're going too fast. So miles per hour. And we don't have to measure speed in miles or in hours, but that's probably what's common. It's what's in our cars, measuring miles per hour. We're talking about the quantities miles an hour and how they change. Sometimes we talk about growth rates. We can talk in a population about how the growth rate increases or decreases over time. You know, sometimes that is important for community planning. Heart rate is another one. And if we were in class together, I'd probably be asking you, you know, what do you think are some common rates of change? You usually measure heart rate in beats per minute, right? So something per something, comparing two quantities. Interest rates or money in general. All right. A lot of times you'll see a lot of applications where we compare money over time, right? And hopefully we want our wealth or our accounts to grow. And others are a birth or a death rate, right? Determining usually just, again, is the birth or the death rate increasing or decreasing versus time? So those are just like some popular ones just to talk about what does it mean to be a rate of change. So what is a homework problem going to look like, or how do I need to apply rates of change? Well, one of them is to be able to use a table. All right, so when we think about the rate of change, as a reminder, is our change in y over our change in x. So let's use the table to figure that out. And I do want to warn you, make sure that like you're checking the entire chart and that there hasn't been a number to throw you off. So I say to myself, h is my independent variable. From 2 to 4, didn't I add 2? From 4 to 6, same pattern. Aren't we adding 2? Same from 6 to 8. So friends, adding 2 is my change in x. Okay, my change in y. If you're wondering, well, if I can't do 76 to 140 or 152 in my head, isn't this the new value? Isn't that the old? So I always tell kids take new minus old. So if I take my calculator, let me clear it out. And if I take 152 and I subtract 76, I get 76. Okay, let's keep seeing if that pattern holds. Okay, so if I take 152 and I add 76, bingo, I get 228. And if I take that plus 76, I get 304. So we keep adding 76 in the table. So adding 76 is my change in y. So that simplifies to 38, and I'm completely okay with that. But sometimes you'll see where we write 38 over 1 because this is a rate of change. So we want to know, well, for every 38 miles, does that make sense? I travel 1 hour. So that's why sometimes you will see it written over 1, even though we know it's 38 and it's not necessary. Okay, let's do it again. So we're looking for our change in y over our change in x. All right, and it doesn't make a difference what column you do first, but notice here on my x's, we're adding 3 to the previous number. So my changes in x are 3. All right, 48 to 96. Again, use your resources if you need them. 96 minus 48 is also 48. Let's see if the pattern holds. So 96 plus 48 gives me the 144. And if I take that plus 48, I end up with my 192. So we're adding 48. That's our change in y's. And so when I simplify, 3 goes into 4 once, 3 goes into 18, 16 times. So 16 or 16 over 1, because basically what we're saying is 16 inches squared, does that make sense, is what we have in one floor tile. Okay, that's what that means. Okay. All right, the graph below shows the number of U.S. passports issued in 2012. All right. In 2012, 2014, and 2016. We're going to find the rates of change from 2012 to 2014 and from 2014 to 2016. We're going to explain the meaning of the rate of change for each case and discuss how the different rates of change are shown on the graph. So when we look at the graph, you can consider this point to be the input 2012, output 13.1. We can consider the 2014 year, input of 2014, output of 14.1. And in 2016, we input 2016 and 18.7. Okay? So if we think about the rates of change, all right, we think about the rates of change. It's up to you how you want to do this, but I'm going to make a table of those inputs and outputs. All right? So we have 2012, 2014, 2016, and we have 13.1, 14.1, and 18.7. Well, the rate of change from 2012 to 2014, we added 2, and 13.1 to 14.1, we added 1. So from 2012 to 2014, my change in y over my change in x was 1/2. Let's discuss what's happening from 2014 to 2016. So 2014 to 2016, we added 2, but 14.1 to 18.7. Okay, let's clear it out. 18.7 minus 14.1, that gave us 4.6. All right, so from 2014 to 2016, my change in y over my change in x was 4.6 over 2, or if you wanted to simplify that, that would be 2.3 over 1. So what does that mean? All right, and I'm going to write out some sentences here. You can abbreviate as you need to, but basically between, right, the years 2012 and 2014, okay, use, when you're trying to explain, let's use the labels they gave you, right? We just listed those years, but isn't our output our passports in millions? So the rate of passports, okay, being issued, I'm using that word from the problem, being issued was 500,000, right? 500,000. Okay. Then from 2014 to 2016, the rate was, now be careful, over that 2-year period, it was either 4.6 million in that period or 2.3 million passports per year. Again, mine is not the only way to say it, but you just remember that these are rates. It doesn't mean that 500,000 were issued or 2.3 million were issued. That was the rate of change. That's how much more. So they were issuing way more passports between 2014 and 2016 than 2012 to 2014. There was definite growth. And how do we know that? How are the different range showed in the graph? Look at the steepness. Look at the steepness from here, right? We're going up 1/2 versus here, we're going right up 4.6 over that 2-year period. And so we have a much steeper piece of the graph. Okay, we're going to determine whether the function is linear and explain. So for a function to be linear, this means your change in y over your change in x needs to be constant. Remember what it means to be constant? It means it needs to be the same. So let's check out our table A. Okay. And I encourage you, I know that a lot of you can do this mentally, but sometimes you can have a tricky problem, and we'll kind of see that in one of our further examples. So just bear with me and kind of do the table work we need here. So, okay. So 1 to 2, we're adding 1. 2 to 3, we're adding 1. And 3 to 4, we're adding 1. That's not really what makes this linear. And it doesn't really make it linear that 6 to 12 is adding 6. So is 12 to 18. And so is 18 to 24. What makes this, yes, a linear is because when I take this 6 over this change of 1, I get a change of 6 over 1. And when I take this 6 and put it over that change, I get 6 over 1. And this change in y over this change in x is 6 over 1. In every case, your change in y over your change in x was constant. That's why this is, yes, it's a linear function. Let's check out table B. Okay, on table B, we're going to do the same work. Negative 10 to 2, I had to add 8. Negative 2 to 6, I added 8. 6 to 4, I added 8. Let's check out the y's. I'm subtracting 4, then I'm subtracting 5, and then I'm subtracting 6. And I know some of you might have that inkling of, oh, yep, that's not a function. Or sorry, not a linear function, but I want to make sure you know why. The reason this is a no is when I take this negative 4 over 8, the change in y over x simplifies to a negative 1/2 ratio. But when I take this negative 5 over 8, it isn't constant. It's not the same as a negative 1/2. That's the reason. Your change in y over your change in x is not constant. That is the reason this is not a linear function. So let's check out C. Okay. All right, so when I'm doing this work, pay attention. Pay attention. Negative 3 to negative 1, I add 1. Negative 2 to negative 1 is, yep, still adding 1. Negative 1 to 1, I'm adding 2. And so a lot of people stop. Let's keep going. 1 to 2, I'm adding 1. Okay, let's look at our y's. 11 to 15, I'm adding 4. 15 to 19, I'm adding 4. 19 to 23, I'm adding 4. 23 to 27, I'm adding 4. When I take this 4 over 1, I get a similar rate of change. When I take this 4 over 1, I get a similar rate of change. But now when I take this 4 over 2, that simplifies to 2 over 1. It is a different rate of change. So my change in y over my change in x is not constant. And again, I know some of you are like, well, if the numbers would change, but let me give you an instance where it would have been. All right, so the change in y over the change in x is not constant. So then this is not a linear function. But if this had been, instead of it being 23, if this number, so let me take these out of the problem. Actually, let me just do a little bit of erasing here. All right. If I would make, instead of this being a 23, let me take those numbers out. If I would have made this 27, Wouldn't have this been 19 to 27 would have been a plus 8? Well, then my rate of change would have been 8 over 2, which is 4 over 1. So I still would have had a constant rate of change. So again, just be careful in your table work that you're determining if it is a linear function the right way. Okay, let's check this one out. 12 to 9 is a minus 3. It appears that, yep, I keep subtracting 3 in this x column. Okay, here I'm adding 5, I'm adding 5, I'm adding 5, I'm adding 5. In all cases, my change in y over my change in x was 5 over negative 3. So your change in y over your change in x is constant. Therefore, yes, this is a linear function. Okay? All right, let's keep going. So I'm sure a lot of you are like, Mrs. Knapp, you keep using this rate of change. It's just the slope. You're right. But when we start talking about graphs of nonlinear functions, so let's say our friend a parabola, something that's U-shaped, we can't talk about slope. So slope really is just a way of talking about rate of change specifically to the linear function. All right, and when we talk about slope, we're talking about non-vertical lines. Remember, we've discussed how vertical lines are not a function. And it is the ratio of change of the y coordinates, we often refer to that as your rise, to the change in the x coordinates, which is your run. So as you move, this is your rise going up and down over how the graph moves side to side. Slope describes how steep a line is. And the greater the absolute value of the slope, the steeper of the line. So just because we have a slope of negative 5, so something that's going down 5 units over 1, it's still steep because we look at its absolute value of 5 to determine steepness. All right, this is just a nice slide that kind of puts everything we just talked about together. Your slope is your change in y over your change in x. We can also refer to it as your rise. How is the graph moving up and down over the run? How it's going side to side. And because a linear function has a constant rate of change, any 2 points on a non-vertical line can be used to determine the slope. I could pick those 2. I could pick the non-corner points, although that's not common. I could pick these 2. You can pick any 2 points on the line to determine the slope. And the formula for that slope is, well, when we talk about what does it mean to be a change in y? A change in y means we are looking at this y coordinate of 1 and this y coordinate of 4, and aren't we finding their difference of 3? And when we want to talk about a change in x, aren't we looking at the changes from 1 to 4, which is also 3? So this particular change in y over change in x would be 3 over 3 or 1 over 1. We're going up 1 over 1 to get to the next point on the graph. We're rising up 1 over 1 to get the next point on the graph. We rise, we run to get the next point on the graph. So our slope formula, you got to know it, memorize it. You will see it on standardized tests. It will be a part of your rest of your mathematical career, is y1 minus y2 over x2 minus x1. Now, it does not make a difference which set of ordered pairs we make to be x1 and y1 or x2 and y2. You just need to be consistent. So here we go. Let's find some slopes. Find the slope of the line that passes through each pair of points. So on A, we just gave you the points in ordered pair form. I am going to label my points. I'm going to choose to make this my x1 and my y1. Remember, ordered pairs come in terms of xy, not xx, not yy. It's x comma y. And I denote the sub ones that's my first set. And I'm going to make this my second set. So this is going to be my x2, y2. So slope. The variable for slope that is used is the lowercase m. And slope is y2 minus y1 over x2 minus x1. So let's fill in those values. My y2 is 5. Carry down that, subtract. My y1 is 2. Write your fraction bar. My x2 is also 5. Carry down this, subtract. Then The negative on the 3 carries. So those are not the same negative. 5 minus 2 is 3. 5 minus a negative 3. The 2 negatives become a positive. So the slope of this line is 3/8. You guys, this is just given to you in table format. I gave you the 2 coordinates, -4, 2. This -4 is paired with that 2. I gave you a horizontal graph. And -2 input is paired with the output of 10. Then I label x1, y1, x2, y2. And if you wanted to, you could do x2, y2 first. Doesn't make a difference as long as you're consistent. So again, I'm going to write out my formula so you can see it. And then fill them in. Y2 is 10. Carry down that subtract. And y1 is 2. x2 is a -2. Carry down that subtract. And then you've got a -4. The numerator of this slope is 8. And -2 minus a -4 means we can actually add the 4. So we get 2. So the slope of the line is 4 or 4/1. I would accept either answer. Some people actually like it 4/1 because that tells me when we start graphing next week that we're going to go up 4 units over 1 unit. Okay, let's do it one more time. So let's be wild and crazy. I can label these my x2 and then my y2. I can label this my x1 and my y1. It doesn't make a difference which pair are the ones, which pairs are the twos, as long as you're consistent. So if my slope is y2 minus y1 over x2 minus x1, let's fill in our formula. This time y2 is equal to -2. Carry down the subtract, and y1 is 2. x2 is a -4. Carry down your subtract. x1 is 0. -2 minus 2 is a -4. And -4/4 equals a slope of 1 or 1/1. Okay. Find the slope of the line that passes through each pair of points. Here we go. Let's do it again. So x1, y1, x2, y2, or you could have done it differently. Okay, so I think we've done enough now that maybe I don't have to write the formula. y2 is -2. Make yourself write a subtract. y1 is -2. All over x2, which is 0, write your subtract, -4. So friends, what's happening here is -2 plus 2 gives you 0 over the non-zero number, +4. Friends, your slope is 0. This is defined. You can have a 0 slope. The example of a 0 slope is a horizontal line. If you think of this as 0/4 or 0/1 or 0 over any non-zero number, that means you're not rising. You're not rising. You're just running. So from this point, I don't go up or down. I just go over 4 units and plot another point. So a 0 slope means that you have a horizontal line. Part E. Let's label. We have x1, y1, x2, y2. So I'm going to take 7 minus 3 over 6 minus 6. Uh-oh. We get 4/0. And what I tell a lot of kids, I don't know if this is helpful, it is okay to have a 0 in the numerator with a non-zero number in the denominator. That's okay. It's 0. But no, it's not okay to have a 0 in the denominator. This is an undefined slope. This means that you have a vertical line. Right? If I have a vertical line, this means I'm running. I can run up 4 units, but I don't go side to side. So an undefined slope is when you have 0 in the denominator with a non-zero number in the numerator. So I like this next graphic. It kind of summarizes everything we've talked about. When your slope is positive, this means that you have a diagonal line that is going or increasing. It's going up from left to right. So if I write my name on the line, it's going up. A line with a negative slope means it's falling left to right. And if I write my name on it, it's going down. When you have a zero slope, that's when we have a horizontal line. And my name is just going across like I would normally write it. And a line with an undefined slope is vertical. And it's really hard for me to write my name that way because it's going up and down. Okay, so this problem is just an application of how we use the slope formula. So we know that the slope formula is y2 minus y1 over x2 minus x1. So they're saying we need to find the value of that x coordinate. They use the variable r, so that when we take y2 minus y1 over x2 minus x1, that we get the slope of -8. So I'm going to go ahead and label my points. So we have x1, y1, x2, y2. So when I use my slope formula, -8, carry down the subtract, -6 over 5 minus r. We have to set that to -8 or -8 over 1 if that's helpful. Well, when we take a -8 minus a -6, we get a -2. And now you have a proportion like we solved in the last unit. So I need to take -8 times 5 minus r, and that's going to equal -2. I'm going to distribute. So I have -40 plus 8r equals -2. We're going to add 40 to both sides. So I get 8r is equal to 38. And when I divide both sides by 8, you get 19 over 4 when simplified. So if you take the slope of 19/4, comma -6, and 5 -8, to keep this video shorter, it's already running long, you can find the slope between those 2 points, and you can check your answer to get -8. Let's do it one more time. Okay. So again, we have our x1, our y1, our x2, our y2. 2 minus 3 over r minus 6 has to equal your slope of 1/2. Well, 2 minus 3 is -1. And I'm going to use cross products to solve my proportion. R minus 6 is equal to -2. And when I add 6 to both sides, I get 4. I'll go ahead and do this one because the numbers are nice. We can check our answers. If I take 2 minus 3 over 4 minus 6, I get -1 over -2, which is 1/2, and it checks. So use the remainder of class time today to refer to 3.3 of your text, and you see the assignment written on this video, and it is also printed in your packet, and it is also printed in Canvas. Make sure you upload your assignment to Canvas when you are finished. Have a great weekend, guys. I'll see you when I return next week.